Hi, this is John Isles and welcome to Geometer's Paradise. Today we're talking about Lesson 2 in Unit 7 called Angle Bisectors, specifically referring to the angle bisector theorem and its application within a triangle. The first thing we want to discuss, of course, is the angle bisector itself. This is an old topic, but it says that an angle bisector is a line or part of a line that intersects an angle such that the line divides the angle into two congruent parts. Simple enough. Our premise in this particular lesson, though, is to go a step further and say that if I snag any point on this line, that it will be equally distant from the sides of the angle. So the angle bisector theorem says what I just said. Any point is equidistant from the rays that form the angle. Equidistant is an interesting word, because when we talk about distance, to or from something, we mean to measure perpendicularly. All right, so to be equally distant, we're going to use a perpendicular to do the measurement. All right, so we get out our tool here, and we're going to draw two lines that are perpendicular to the sides of the angle from the point we select on the angle bisector. And if you look carefully, you should see the beginnings of our proof as well. So equidistant means perpendicular, so these two segments are perpendicular. Our goal is to show that this is congruent to this, and we have two angles and of course a reflexive side with which to work. So this is an angle side, and then a CP/CTC. All right, the angle bisector theorem is used by making calculations based on the fact that we have an angle bisector. So here, AB bisects angle GAH. Now, because AB bisects angle GAH, we can say that 7x plus 18 is equal to 12x plus 3 because of the angle bisector theorem, and that is AB bisecting angle GAH. This second bit is just notation for me and for you. It kind of helps us remember, well, where's the ABT coming from? Well, AB is bisecting GAH. Of course, subtracting 7x from both sides gets us 5x, and subtracting 3 from both sides gets us 15. So x is equal to 3. Now the measure of GB then is 21 plus 18, which is 39 units. And the measure of BH is 36 plus 3, which is 39 units. A little more geometrical is the proof for the angle bisector theorem. We begin by drawing perpendiculars from B to the sides of the angle. So here's 1, here's 2, and we label those perpendiculars D and C. It really doesn't matter which one is which. Okay, so here we are. We have our perpendicular line segments. Okay, and this is an angle bisector. So here's our given, and then we'll grab the reflexive side. So angle DAB is congruent to angle CAB because of the angle bisector. And then angle ADB is congruent to angle ACB because we have perpendicular lines forming right angles, and all right angles are congruent. So we'll just say perpendicular lines. And then we have the last side. This is AB, congruent to AB by the reflexive property. From here, triangle ABD is congruent to triangle ABC, angle side, and that means that DB is congruent to BC by CP/CTC. That's corresponding parts of congruent triangles are congruent. Okay, the converse of the angle bisector theorem says that any point that is equally distant from the sides of the angle, now remember, equally distant implies perpendiculars, so these lines here are also perpendicular to one another. Okay, this implies perpendicular. All right, they must lie on the angle bisector. So here we are. We draw the angle bisector, or no, we draw a line that goes through the point, and we prove that it's the angle bisector. Of course, we have this segment, so we're looking at hypotenuse leg for this proof. All right, here it is. We're going to draw a line segment AB to begin. And by reflexive side, so the right angles, we say that angle AGB and angle AHB are right angles because of the whole equidistant perpendicular line thing. The hypotenuse is that AB is congruent to AB by the reflexive property, and that GB is congruent to BH because that's given to us. So triangle AGB is congruent to triangle AHB by hypotenuse leg. Now, CPCTC is going to allow me to say that these two angles are congruent. But that's not the answer to the question. The answer to the question is it a bisector? And of course, if this line segment divides GAH into two congruent angles, it is. So AB bisects angle GAH by definition. So what's the importance of this? Well, it turns out that the angle bisectors of a triangle meet at a single point just like the perpendicular bisectors of a triangle do. So if I were to draw the three angle bisectors, whoops, a little too far. It'd look like this. All right, now, they're concurrent at a point then. If I go a step farther, I draw, so here they are, the angle bisectors, and then I can draw three line segments that are altitudes. So I'm going to draw three altitudes from D. There's 1, 2, 3 altitudes. Now each of these altitudes, of course, is perpendicular to the opposite side because it's an altitude. Okay, but what we want to do is show that these segments are congruent to one another. And we can use the angle bisector theorem to do that. See, DA bisects angle CAB. That means that D is equally distant from both endpoints. So we say, oh, this is X, this is Y, this is Z. We say DX is congruent to DZ because of the angle bisector theorem as AD cuts angle CAB. And then we can say, we can do it again over here for CD. DX is congruent to DY. This is again by the angle bisector theorem. This time CD is cutting angle ACB. And finally, we can say that DZ is congruent to DY, and for one of two reasons. First of all, the transitive property, DZ is congruent to DX and DX is congruent to DY. Or we can do the angle bisector theorem because again DB is bisecting the angle ABC, which means DZ and DY are congruent. DB bisects angle ABC. An interesting consequence of the angle bisector theorem is that this point is equally distant from the sides, which means that, we can go in there and we can draw a circle inside the triangle so that it intersects all three vertices. And this is called an inscription. Inscribe, remember, scribe means to draw. In means, of course, inside. So to draw inside. So here we have the angle bisector as an inscription. This contrasts with the perpendicular bisector. Okay, remember the perpendicular bisector sectors of a triangle also intersect at a single point, and its name is circumcenter. Circum means around. So the circumcenter is a circle drawn around, and the point, the center of that particular circle is at the intersection of the perpendicular bisectors. The angle bisectors, however, the angle bisectors meet at a point called the incenter, which allows us to draw a circle inside of the triangle. So the incenter inside. Okay, and here it is. We're just saying that the incenter is the name of that point. Okay, and then we can use the incenter. So again, if we know the measures of these angles, we can set up some equations. For example, here, well, let's call this x, y, and z here for clarity. dy and dz are congruent to one another because of the whole incenter thing. So d is the incenter. That's the given. D is the incenter. So 20x minus 14 is equal to 12x plus 50 by the incenter theorem. Okay, so we got 8x over here and 64x, or 64, so x is 8. And then the measure of this is what? This 160 minus 14. So this is 146 units. Then 4y plus 2 is equal to 146. 4y is equal to 144. So y is 36 units. All right, there you go.